I'd like to welcome all of you to the Simon Center and to this Della Pietra lecture. It's really a great pleasure for all of us at the Simon Center to see so many loud, enthusiastic, energetic high school students. I think you're in for a treat today. I'm sure you're in for a treat today. Today's Della Pietra lecturer is Tadashi Tokieda. He is a director. He is the director of mathematical studies at Trinity Hall, which is one of the colleges at the University of Cambridge in England. And he is currently a distinguished visiting professor at Stanford University, so he didn't have to come too far to come here. He is very well known, quite renowned for his talks on mathematics, and especially mathematics in everyday things. He uses everyday objects, toys sometimes, to illustrate basic mathematical principles and begins to analyze them from a mathematical point of view, both illustrating the underlying mathematics and helping you understand better what you're seeing or experiencing in these everyday objects. His talks are incredibly engaging and a lot of fun, and sometimes even have a little magic in them. So maybe we'll see some magic today, I'm not sure. Anyway, please welcome Professor Tokieda and enjoy the talk.
Good morning. In case I start speaking funny, that's because I'm not really used to English. I learned English quite late. And you know, during a lecture of this type, this is in fact not a lecture, it's a rather magic show, people tend to feel shy. Sometimes I wish that some people are a little more shy than, but anyway, so people tend to feel shy and they don't ask questions. But in this particular case, please make an exception, because English, in the order in which I learned the language, is my seventh language. So, you know, I might start talking funny and you may not understand what I'm saying. It's almost certainly my fault. So if you can't hear anything clearly, or if you don't understand something that I'm saying, please raise your hand or even shout and then stop me, and I'll try to do that better. Okay. Can I have the camera, please? I'd like to show you a little magic trick, in fact, a sequence of magic tricks, and the motivation, should I say, the background is as follows. You know, I'm currently working as a professional mathematician, research mathematician, and when I meet people and they ask me, what do you do in life? And I say, I'm a mathematician. They say, oh, you must be multiplying bigger and bigger numbers together faster and faster. That's a funny thought. You know, when you meet a novelist, for example, you don't say, oh, you must be practicing writing letters of the alphabet bigger and bigger, faster and faster. Right? I mean, what do they think? Do they think? But there is a reason for people's reaction like that. The reason is that, you know, in schooling, which all of us are subjected to, and enjoy sometimes, there is a big difference between, say, English and mathematics. In English, you first learn to read and write. To be sure, you have to do this. But then soon enough, you start reading interesting literature, interesting books, and you might even start writing interesting things. And by the time you graduate from high school, for example, you are quite close to being full-fledged adults, and some of you actually are. In mathematics, that's not the case. It's a bit like learning to play an instrument, a piano, for example. There's a fairly long technical phase during which basically you are learning to multiply bigger and bigger numbers faster and faster. Or if you don't deal with numbers anymore, especially in high school, you might be dealing with formulas. Yeah? You are multiplying more and more complicated formulas faster and faster together. Okay. But you can imagine that there's more to this. And in particular, there's more to calculation. When we think about calculating something, you know, most people think that mathematics is synonymous with the same meaning as calculation. Well, you think of numbers, calculating with numbers, and calculating with formulas. But I'd like to show you that actually calculation is really a weird beast and a mysterious one. You can calculate with lots of other things that are neither numbers nor formulas. Take a strip of paper, yeah, and I bend it in should I say, an S shape like this, or Z shape if you like. Yeah, do you see what I'm doing? And with the help of two perfectly ordinary paper clips, I'm going to fix that S shape by slotting the paper clips here and here. Do you see what I'm doing? You probably see better on this screen. So here and here. Yeah, so that's the preparation. That's the shape. And there's a paper clip here, and on the back, if you like, there's a paper clip here. Everyone cool with this? Okay. Now, what happens if I start pulling the ends of this strip? Well, you can see that the paper clips come closer and closer together because they're being driven by the paper. Yeah? So if I keep pulling, the paper clips will eventually touch each other and jam. But if I keep pulling nonetheless, they hop. And when I pick up, they are linked together. Professor Abanov, can you come over here? If you clap at this stage, I don't know what you're going to do next. But can you come here? I'd like to hire you. I'm sorry, I hadn't warned him that it was going to happen. Professor Abanov is the Deputy Director of Simon Center. I'm sure that everyone here is thinking, Tadashi has cheated, of course. So I'd like to have him do this. Would you like to do this? And this is the kind of thing, you should do this at home immediately because you think that it's simple to watch, and it is simple, but you have to do it just once yourself in your life. And then for the rest of your life, you can show this off to friends and family. So what he has just done is to bend it in an S shape or Z shape. And okay, he's a very good scientist. He has very observant and quickly understood. Put paper clips here, here and here. Okay? Is that all right? So you imagine this S shape, and then you fix the shape with two paper clips. Now, you can pull it, please do, slowly, fast, it doesn't matter. I designed it so that whatever rate that you pull, poof, and they pop, and you can pick it up because I didn't touch anything. They are linked together. So thank you very much, Sasha. That's very nice. Well, if our scientific careers don't work out, we can start a factory that links paper clips together. And so this is what it is. Now, this trick was actually discovered by somebody, I can't really find out the legendary prehistory of this, but the earliest reference that I find is, bless you, Gardner's, Martin Gardner's Encyclopedia of Impromptu Magic, and it references somebody called Bowman from Seattle who started doing this in the 1950s. But I now would like to show you a whole sequence of variations on this. I'm going to prepare exactly the same configuration, so this S-shaped curved thing with two paper clips fixed in the shape, with the addition, however, of a rubber band. Do you see this? I hope you can. Yeah. It's hanging here. If you see what I mean, this paper, which I have curved, has two loops here and here, two holes. This rubber band, seen from your side, is hanging on the left, not on the right, on the left. I'm being a little picky because in a moment I'm going to hang it from the right and then call it something else. But this one hanging from the left on your side, which I call version number 1. Version number 1 of this. So, okay. This time, when I pull, what's going to happen is this. Did you see that? You have this rubber band paper clip together hanging from this sheet of paper. That's quite good. You have this half chain, and you'll see later on why I call it half chain, of rubber band clip linked together. That's quite good. Well, I need not preach to most people here that in science you have to exercise the power of observation. What I mean is, things might look the same, but you can't dismiss as a priori irrelevant tiny differences of innocuous appearance. You can't say, oh, what difference does it make? Or it's all the same. No, it doesn't work that way in science. You have to be very careful when you do science. So I'm going to give you another variation of this. And in order to do this, I have to make sure that I'm bending it in the right way. Let's prepare almost exactly the same thing, which looks really like the same thing as version number 1 that we have just tried, but which is not. Version number 1 that we have just tried is this one. You remember? There are two holes or two loops, and the rubber band was hanging, as seen from your side, on the left. All right? That was version number 1 on the left. Now, suddenly the rubber band is hanging on the right, not on the left, and these switch are called version number 2. Okay, so now if you're not observant, you might say, oh, what difference does it make? I mean, left, right, it's the same, but you remember what happened to version number 1. Version number 1 ended up having the rubber band hanging from the strip of paper with 2 paper clips hanging underneath, yeah? This time when I pull, the whole thing falls off the paper. It doesn't hang onto the paper, so it is different. It is different, nonetheless, this half chain, what I call the half chain, of clip rubber band is still present, so it fell down. Okay. Thus, version number 1 stays on the paper, and version number 2 falls off the paper. Having seen 1 and 2, it becomes tempting, indeed irresistible, to do both of them at the same time. What happens if I do 1 plus 2? 1 plus 2 at the same time. I think all of you, and very luckily I have brought another rubber band. How lucky is that? And I'm sure most of us here will agree that 1 plus 2 should mean this configuration. Here we have, again, 2 loops of the paper, and this one is hanging on the left, and this one is hanging on the right. You see that? Okay. This one by itself was version number 1, if I didn't have the other one. And this one by itself is version number 2 if I didn't have the other one. So this is 1 plus 2. So what's going to happen if I do 1 plus 2 at the same time? Before we do that, let me debunk myself. Part of this magic is actually not all that surprising. You know, the fact that the paper clips come together and link, that's actually quite an interesting thing, and it's worth studying a little more and then investigating how we can apply this and so on. But the fact that in version number 1, the rubber band stayed on the paper, and version number 2 let it fall off the paper, that's no mystery, it turns out. So I'm going to try to explore why that is, of course, the case. You see, forget about paper clips. You remember that the version number 1 had the paper curving like this and the rubber band hanging here. You see that? Okay. If you look at how the rubber band is positioned with respect to the paper, you see that the paper goes through the rubber band but comes out and goes on the side, and that's it. So the rubber band is linked with the paper. It's hooked onto the paper. Yeah? So if I pull the ends of the paper, of course, because the linking is there, the rubber band has no choice but to stay on the paper. Did everyone understand that? Okay. In contrast, version number 2 looked like this. 2 loops and the rubber band's hanging on the right. And you see that in this case, the paper goes through the rubber band but comes back out. Do you see this? Rubber band is here. Maybe the contrast is not that great, but it's, do you see that? Or maybe this is where you see. So the rubber band is not linked with the paper. When I pull, because it's unlinked, it's free to fall, and so it does. That's why in version number 1, the rubber band stays on the paper, and number 2, the rubber band falls off the paper. So that's no mystery. As I say, somehow the game that the paper clips are playing, especially with respect to linking or not linking with the rubber bands, that's really interesting, and we shall probably come back to that later on. So let's go back to where we left off and do 1 plus 2. What is 1 plus 2? A quick revision. You recall that the version number 1 by itself, a single rubber band hanging on the left and 2 paper clips, had the result of rubber band hanging from the paper, clip underneath. Yes, that's number 1. Version number 2, what did we have? Clip rubber band, but everything fell off the paper. So what do we get if we do 1 plus 2, 1 plus 2, 1 and 2 at the same time? Any takers? Yes, and lady there. So the lady here, what's your name? Marita. Marina. Yes. Oh, okay, Marina is really smart, and she also is courageous. She's willing to guess, she has a certain mental picture, and she commits herself. I'd like to advertise to you the fact that when you do science of any kind, mathematics in particular, but any science, and in fact, life in general, you should always guess before you start solving any problem. Because, if you guess right, then you are very proud because, your friends think you're smart and so on, and you're very, very happy. And if you guess wrong, well, that's a golden opportunity for learning something. Why was it wrong? what was wrong with my picture, and then you become smarter afterwards. So always guess. It's a great way to commit oneself. If the money is at stake, you really are serious about something, right? Well, guessing is a bit like this. Your sort of intellectual pride is at stake. So Marina says that what we should have is rubber band hanging from the paper with clip rubber band. Do people agree with this? Does that look fairly reasonable? Because, well, it's reasonable, right? Because number one just had rubber band clip, and number two clip rubber band. And if you merge or fuse them, surely you get rubber band clip rubber band. Now, Marina, surely that's too simple and natural to be true. I mean, you are dealing with a magic show. However, sorry, you have something? So what's your name? Sylvia. Sylvia asks whether I get, sorry? Sophia. Sophia asks whether I'm going to link the rubber bands. No, I do that only for money. Not today. And so, another kind of show, in a dark and seedy place. But let's go back to the first guess. So rubber band, clip rubber band. Now you're going to say that's of course the simple or the first guess that comes to mind. It's very natural. It's too simple and natural to be true, you might say. But you see, you shouldn't approach science like this. If you say, it's too simple to be true, so it's probably something more complicated, well, you are trying to second guess the magician. And if you have a human-to-human relationship like this interaction, magician to the spectators, or maybe a lawyer to the clients and so on, or whatever, you second guess what the other person is doing because you are competing against other humans. But here, what we're doing is actually part of nature. You can do exactly the same thing at home. In fact, right here, if you get bored with my show, you can start doing your show in your row. And you can try, and exactly the same thing will happen. So the point of my message is that actually nature is really simple and, as we say, natural. You should just guess, go for the simplest natural solution, and almost always nature obliges. Yeah? So you shouldn't try to second guess. You should try to start twisting your mind. Nature is not a mean human being. Nature is a very gentle, sometimes austere, but really a straightforward creature. So let's do this. 1 + 2. It's probably too simple to be true if I were running the show, but I'm not running the show. Actually, Mother Nature is not running the show. So let's go. So this is 1 + 2, left and right. I'm going to pull the ends of the paper. And what happens is, of course you are right. Of course this happens. Rubber band, clip rubber band, the entire thing hanging from the paper. We should applaud people who have guessed that. All of you who have guessed that. Of course that's what happens. So we have, now you understand why I had been calling the earlier results half chains. You have now full long chain of band, clip, band. Yeah, the whole thing. And it makes sense because this one, which ended up hanging, was the rubber band that came from number 1. Yeah? And so it was hanging on the paper. It was linked to it, but it had no choice but to stay on the paper. The other band, number 2, was unlinked with the paper. So it could fall off, and so it did. In between, you have the paper clips. If you didn't have this rubber band, you see the result that we obtained is exactly the familiar result of number 1. So rubber band, clip hanging from the paper. And if we didn't have the top rubber band, well, look, you get clip rubber band, but it's not connected to the paper, so of course it will fall down. That would have been number 2. And together, of course, 1 + 2. Of course, that's what happens. So you get this long chain. And from now on, for a few more instances, we'll get this long chain appearing of band, clip, band. Okay. We have tried 1 + 2. Well, what about 1 + 1 then? 1 + 1. So let's do 1 + 1. And that means that we have to get 2 copies of number 1 into the picture. How do we do this? Well, that's easy. You again bend the paper always in the same configuration. That's the same. And I'm going to put number 1 in one position. And another copy, shall I say, of number 1 in the other position. And I'll show you what I mean by a copy. Look. If you see it from your side, here is the familiar position of version number 1 hanging on the left loop, yes? There's another rubber band in this position. Do you see that? Yeah. This top rubber band, as you can see by rotating and seeing from the back, is another copy of number 1. Do you see this? So that's a number one, and that's another copy of number one. And each of these number one copies, number one rubber bands, is linked to the paper. As you can see, the paper goes through one, goes through the other, and comes out. So they are both linked with the paper. Those rubber bands must stay on the paper. Yeah, we all understand this. Now then, what's going to happen if I pull the ends of the paper? What kind of thing are we going to get? I can whisper to you as a hint that we still get the long chain of band, clip, clip, band. But the question is, how is it going to be positioned with respect to the paper to the table? Any takers? 1 + 1. What do you think happens? You have, I'm going to get somebody from far back. Well, there is one person who went up.
It would be like the 2 paper clips, and then the rubber bands are together.
What do you mean by together? You mean the rubber bands get linked?
They're both there's no hole. They're both linked up to the same clips.
So the idea seems to be that you have a clip, one clip in the middle, and then 2 rubber bands, so rubber band, clip, rubber band. And then where does the other clip go?
No, it's clip.
Yes.
Clip, and then both the rubber bands.
But what do you mean both rubber bands? You mean 2 rubber bands will come through each other and get linked? Is that what you mean?
No. The rubber bands they're both same length. Like they're both hanging from the same.
Paper clip.
Oh, I see. So I think, what's your name?
Dylan.
Sorry? Dylan. Okay. So Dylan says maybe clip, clip, and at the bottom clip you have 2 rubber bands hanging from the same clip. Yeah? Okay. That's an interesting guess. You have no. Look. I told you you must guess. I told you must guess, and in fact it is, what I mean by interesting guess is an interesting guess. It is, no, I'm not making fun. You know, she has a certain mental picture, and we are going to try if that mental picture is exactly what nature does. If it does, so much the better. If it doesn't, even better, because he's going to now become smarter and will understand better how nature works. So there is somebody in the far back, that lady there.
Rubber bands, then 2 clips, and rubber band, and both of the rubber bands.
Okay, so the lady in the back, what's your name?
Kaya.
Kyle?
Kaya.
Okay, Kaya. Kaya says that you would have a long chain of rubber band, clip, clip, rubber band. In fact, that's what you're going to have. But 2 rubber bands will be hanging from the paper. So what's the only possibility? You'd have a paper strip there, rubber band hanging there, and rubber band hanging there, and in between there are 2 paper clips connecting those rubber bands, but sort of hanging in the middle. Yeah? Who agrees with this kind of guess? Okay, congratulations. This is the guess that most reasonable people go for. But you know, you have to. But you have to be careful, because you know what we humans think most reasonable are not always what nature does. So we have to be ready. We have to be open-minded enough to correct our intuition. Okay, let's do this. By the way, I would like to make sure that we all understand that whatever the clips end up doing, yeah, they mind their own business, but as far as the fate of the rubber bands is concerned, they must both stay on the paper. Yeah, there is no choice. Rubber bands must stay on the paper because both of them are linked with the paper. They can't leave. Okay, so the only question is, how will the paper clips interact with the rubber bands? So this is 1 + 1. Thank you very much for waiting. 1 + 1, I pull the ends of the paper, and you think that, for example, Kaya thought that this would happen. Many people thought that something would happen. Yes, indeed, this is what happens. So you get, no, you are close. It's true. You are very close. I think I know where your picture came from, by the way. So what we get is some sort of suspension bridge, yeah, with 2 rubber bands on the paper, as we knew would happen. But in between, there is sort of a connection between those 2 rubber bands with paper clips. So you get rubber band, clip, clip, rubber band. Now, do you agree that probably all of you in this room have never seen this done before? Yeah? Nonetheless, you knew more or less what was going to happen. Yeah? So you have calculated. You've calculated something. You didn't know what you were calculating. You didn't have any numbers in front of you, let alone formulas on a sheet of paper. But somehow or other, your brains caught on to this part of nature, maybe mathematical part of nature, and understood. Even if you are doing this unconsciously, even if you are all intuiting, nonetheless you calculated. That's really weird. You have never seen this before, but you could predict with a fair degree of certainty what was going to happen. So 1 plus 1 is like this. And because you see, in the case of 2 plus 1 or 1 plus 2, 1 was hanging on the paper, 2 left the paper. 1 plus 1, both of them stayed on the paper. So that's the only difference. It remains for us to try 2 plus 2. Thank you very much for pointing that out. So let's do this. 2 plus 2. Now, 2 plus 2, what was 2? 2, I'd like to recall, is the version which by itself left the paper. Okay? So, what is this by way of 2? What am I doing? I'm going to do it like this, I think. So, I'll put my rubber band here. And the rubber band here. Okay. 1 plus 1 looked like this. Do you remember? Yeah. And you please make sure that both rubber bands are linked to the paper. That's 1 plus 1. 2 plus 2 is this. Do you see the difference? So in the usual way that I show, this rubber band is hanging on the left loop, and as you can see from the back, that's another copy of number 2. And so they are like this. And you agree with me that if we didn't have the top rubber band that I'm holding, if you had only the bottom rubber band, look, the paper goes through the rubber band and twists over and comes back out, so the bottom rubber band is not linked to the paper. So if I pull, it should be able to leave. And similarly, the top one, the paper from here starts coming in but comes back out, so it's not linked to the paper either. So what's going to happen if I pull the ends of the paper? I'm going to ask for opinions. Yes, you have a... Yeah, so rubber band, clip, clip, rubber band, and... Okay, what's your name? Kate. Okay, Kate suggests, she has a mental picture, that you get still this long chain of rubber band, clip, clip, rubber band, and I can guarantee to you that that's what's going to happen. We are going to get. But what's going to happen to this long chain? Well, neither of these number 2s is linked to the paper, so the whole thing will just drop down to the floor, to the table. Who agrees with Kate? Now, good. When I was first discovering this, because I discovered this, somebody has to discover everything that you learn, and then it becomes the common property of all humankind. But somebody. So I was making this modest discovery, exploring and certainly guessing every time, and often being proved wrong. And when I was discovering and exploring, of course that's what I guessed. Yeah, long chain. So let's try this. This is 2 plus 2. Yeah, nothing up here, nothing up here. Okay, 2 plus 2. Yeah. Each of these is unlinked to the paper, so the entire thing should fall down. Are you ready? I pull the ends. But this time, our intuition doesn't agree with what nature does. The whole thing stays on the paper, but the way it stays on the paper is rather extraordinary. Let me show you how it did. And I'm not sure that we have enough resolution on the camera to do this, but let's try this. Okay, do you see what I'm holding here? Okay, so there are 2 rubber bands. Please ignore the paper clips. They're not that important at this stage. You see, there are 2 rubber bands. There's a rubber band that goes around like this. Goes around like this. Yeah. And there's a rubber band which is hooked in the middle like a lock. So if we didn't have this rubber band that goes around, the lock that's hanging in the middle can fall down. Okay. On the other hand, if we didn't have this middle lock hanging, well, nothing stops it, so we can pull this rubber band from the side. So what we have here is that neither of those 2 rubber bands is hooked onto the paper, but each one is preventing the other from falling down. So if we think of the paper as the last loop and close the loop, here we have a system of set of 3 loops that are hanging together, interlocked, but any 2 of them are not interlocked. Can I have the slides, please? And that object has a name. I drew a cartoon picture here of what we get. You see, that's a rubber band, and that's the rubber band, and there's a paper that I close into a loop. This kind of object is called a Boromian Link, after the Italian Renaissance family from northern Italy, Borromeo. No, that's not a family who used to poison one another. That's Borgia, that's another family. Boromian Link, Borromeo. And because this configuration, which I drew a more abstract cartoon picture thereof here, you see there are 3 circles that I drew here, and they're interlocked. You can't take them apart. But if you look at any 2 of them, you can take them apart. For example, suppose that I eliminate, in my mind's eye, go kazam, and then make this disappear, this one. Then you can see that this one is just sitting on top of that one, right? So they can be pulled apart, if not for this third one. Next, let's imagine that I make this one disappear, kazam. Then you can see that this one to the left is just sitting on top of this one to the bottom. So you can pull them apart, if not for that third one that's preventing that from happening. And finally, if I make this bottom one, boom, boom, kazam, and make them disappear, then this top right one is sitting simply on top of the left one, so you can pull them apart, if not for the third one that's preventing them from happening. So you can see that this one is sitting on top of this one, and this one is sitting on top of that, but this one is sitting on top of that one. Yeah, this on top of this, on top of this. So it's a bit like rock, paper, scissors. It's like a topological rock, paper, scissors, if you like. So this is a remarkable configuration, which was used, I don't know if you can see, very, very tiny, as the coat of arms of the Boromian family, here. Here, they drew this. So it is a remarkable configuration. So they're all locked together, 3 of them, but you can take apart any 2 of them if you make the third one disappear. It's quite metaphorical, isn't it? Everywhere in the world, especially in the physics and mathematics community, this is called the Boromian Link, but actually this motif appears in other cultures as well. I know personally of Miwa Shrine. It is the Shinto shrine in Japan, in the prefecture of Nara, just south of Kyoto. And the foundation of this shrine is shrouded in legends, but it's certainly before the 5th century. So it's more than 1,500 years ago, and so 1,000 years older at least than Boromian. And in this shrine, it's actually a funny shrine. You know, when you go to a temple, a shrine, or church, and so on, there's usually some main part, and then there's an altar or something. It's the holy of the holies, and you go there and worship and so forth. But in this Shinto shrine, you enter this big shrine made of wood, and then there's a first gate, and there are some buildings, but it's not yet the main part of the shrine. So you go in, and you wonder where the god lives, and then so there are some shrines, and so. And then there's another gate, you go in, and you just keep going, and then you come out in the back and just facing the mountain with the forest. And it turns out that the main thing to come and worship is the forest and mountain. So that's an interesting thing. But anyway, the coat of arms of this shrine is actually that Boromian Link. And Miwa in Japanese means 3 links, 3 rings. So there are some other examples of this. And here I have brought one curious object. Can I have the camera, please, now? Which is made of wood. I don't know if you have seen this. I wish that I had brought a larger one. I have a much larger one at home. And this is a collection of 3 pieces of wood. Sorry, I'm going to hold it like this. And with the curious property that if I make any one of these disappear, 2 of them can be pulled apart. For example, if you imagine making what I'm holding vanish, then this one and this one can be pulled apart, right? And it's the same with any of the other 2. So I bought this in Africa, and you can often buy this in souvenir shops and markets and so on. And when I was first told that this was carved out of a single piece of wood, I was very impressed. But then I realized that that's the only way to make such a thing. Of course, I can't do. Okay, next. So you can put it on the floor and then hold, for example, a pot or something like this. Now, let me show you another thing. I'm going to hold it here. I have brought here 2 loops. Can you point to me? And I'm trying to pull back so that you can see the whole thing. Yeah, that's right. And I should stand here, right? Okay. I brought here 2 ribbons into a tied into loops. So I'll hold them like this. Do you know what I'm doing? Like that. Okay. So I should stand here. There are 3 loops here: the blue one, pink one, and the loop made by my fingers. Okay. And you probably think, and I think so too, that the blue and the pink are linked, because indeed they're hooked together, they seem. And pink and my finger loop are linked. But my finger and loop and blue are not linked because they're far apart in space. Yeah? You agree? So blue is unlinked, but pink is linked with my fingers. But now I'm going to grab this part and then pull, and then they exchange places. Now, pink is unlinked with the fingers, but blue is linked with the fingers. What happened? I mean, they exchanged places and they changed topology. But I can keep doing, and then we are back to where we started. You can just grab this strand and keep pulling, and it's very meditative and zen. You can keep doing this. And it's very, very strange that one time pink is linked and pink is unlinked and blue is linked, but the next time blue is unlinked and pink is linked and so forth. The fact of the matter is that they're both unlinked with my finger loops. In fact, any 2 of these are unlinked. This is one interesting presentation of Boromian Link that we have seen. I'll convince you of this because, you see, clearly, if I get rid of my fingers, boom, make them disappear, you can unlink you can take apart, pull apart the other 2, right? So that's no problem. Also, sorry, I've also I've undone the loop. I'm going to, please give me a few seconds until I tie this again. And tying the knot, that's very, Valentine's Day is coming. Okay, so they can be taken apart. On the other hand, clearly, if you get rid of the pink, I can unlink my finger and I can take apart my finger and the blue, of course, if you just cut it here. And finally, if I get rid of the blue, look, if the blue were not obstructing that operation, sorry, I should go here, I can pull the pink out of my finger loop. So any 2 of those loops are unlinked, but 3 together are stuck together. So this is one more presentation of Boromian Link. Can I have the slides, please? And Boromian links have some relevance to our life, and a rather sinister one, I'd like to point out. So I want to share this secret with you so that you are careful. One example, I don't know if anybody like here climbs mountains and so on, scales mountains. If you do alpinism, mountaineering, there are some gadgets that you use. So there's something called a piton, which is sort of a big, giant nail that you drive into the rock and so on, and you also have pickets. But another gadget that you often use is called carabiners, or carabines. Carabiner Haken in German originally, and carabines. They were invented by Alpine people. And these are basically sort of snapshot locks. I showed you some pictures. It has a little thing that flaps out with a spring action. So if you want to have connect it to some link, you just snap it and these snapshots and it gets linked. On the other hand, if you want to unlink it, some human has to deliberately sort of move it over and then unlink it and remove it. Yeah. So these things are always designed so that it's easy, very, very easy, almost spontaneous to link, but very difficult to unlink. Because, don't you agree? People believe that, of course, more links there are, the safer you are, hanging from, for example, a system of ropes and carabines from the top of the mountain. You agree? Yeah, more links, more security. But that's not true. Imagine that you have some sort of combination of ropes and carabines which look like a Boromian link. Yeah? And suppose that you're hanging for your dear life here, and from the top of a mountain, you're being suspended at the top of this circle here. Yeah? You're suspended from above, and you're hanging here. And let's say that, okay, I'm going to make myself safer, more secure. You see, those 2 are not linked. So let's link them, and suppose that there's something like a carabine, and you can snap them shut and link them suddenly. What I mean is to exchange those 2 strands into this. Having done this, of course, this ring and this ring get linked now. So that's very good. Carabine linked those 2 rings. Are you safer? No, because, look, this one can be brought over to this piece. And you see, this picture and this picture are the same pictures. Can you see this? You shrink this, and then you bring it over here. And so you can make this picture into this picture. I don't know if you can see. Yeah. This one can be shrunk and brought over here. And look, now this is completely disjoined and linked with this one. So if you're holding here, you fall down to your death. Just because you took two things that were unlinked and linked them together. So it's not true that the increasing linkage increases your safety. This phenomenon is known to some Russians. I mean, in the Russian literature, this is known, scientific literature, it is known, but it's not widely known in the rest of the world. So you should be really careful. If somebody says, for example, in the design of any kind of networks and any kind of sort of rope structures and so on, that, oh, we're going to link more, and then that will sort of secure the whole thing, it may not be true if there's a Boromian link hiding somewhere. Okay. Good. Can I have the camera, please? Well, if you want to show this to friends and family, I'm going to finish in a moment. I suggest that you tease them a little by doing the finishing on the following note. You tell them, okay, folks, you have understood everything, right? And by this stage, you feel that way too. You are feeling really confident and cocky. Yeah, we have understood everything. We have seen everything. And so you say, okay, let's revise the first thing from which I started. Let's bend the paper into an S shape and then fix the shape with 2 paper clips. And you're saying, oh, we have already seen this. Yes, I know what's going to happen. Okay, so what happens if I pull the ends of the paper? You say, well, of course they get linked. Well, that's really funny because not more than 30 minutes ago, nobody has seen 2 paper clips link, but now people think that they always link. But anyway, so you take this, and then you pull. What's going to happen? You know that they're going to be linked, right? But no, they didn't get linked. What happened? Huh? What happened? I pulled and they didn't get linked. Well, because people are being distracted by my chatter, what I did, some of you observed, is that I put certainly one of the paper clips at the top of the paper, but the other paper clip not at the top, but at the bottom of the paper, like this. At the bottom and at the top rather than top and top. So they're on wrong sides of each other. They have no incentive to link, of course. So you have to be a little careful. You have to watch. This is not just a piece of meanness to your spectators at the end of the day. You can actually start doing science again. You see, you can now place the paper clips in the wrong positions, quote unquote, but with rubber bands. What's going to happen, for example, if I do 1 + 1, but with paper clips in the wrong positions that don't link? Let's do that then, and we'll see what happens. That's what it is. You remember this is 1 + 1 configuration, so both of the rubber bands are linked to the paper, so they have to stay on the paper. But this time, unlike the previous experiment of 1 + 1, which seems like a long time ago, there's a paper clip here at the top, but behind there's a paper clip at the bottom, not at the top. So the paper clips will not link, will not join. But the rubber bands must stay on the paper. Now, what do you think happens if I pull the ends of the paper? Somebody who hasn't, would you like to, far back, sorry, over here, the red gentleman.
One rubber band's going to it, the rubber band's going to be separate.
Yeah.
And there's going to be one paper clip attached to each.
Okay, so what's your name?
Russell.
Russell says, Russell, right? Okay, says that you imagine a paper strip of paper, and then you get rubber bands hanging from the paper strip. Of course they have to, because they're in position number 1. Yeah, topologically there's no choice. But he says the paper clips will not link this time. Do you remember what happened to 1 + 1 when we had the paper clips in the right positions next to each other? Well, you had this suspension bridge, right? All he's saying is that, well, paper clips will not link this time, so let's imagine that suspension bridge and cut the bridge in the middle. And so what you get, yes, you've seen it, rubber bands hanging individually, and one paper clip on this rubber band and the other paper clip on this rubber band, so they'll be hanging like this. Yeah? Who agrees with this? Okay, so let's try doing that. So these are both number 1s, and then I'm going to pull the rubber band all together. And then what's going to happen? Oops, sorry. That's very interesting. You see, topology can go wrong sometimes if you do this kind of thing. Okay, let's do that with another sheet of paper. I'm going to do that again. and then we'll finish in a moment. So, clip, rubber band, and paper clips in the wrong positions. Okay, so this is, again, 1 plus 1, sorry. This is probably a better configuration anyway than before. And the paper clip at the top, but the other one is at the bottom, so on the wrong sides of each other. Now, Russell says you straighten the paper and you have rubber band hanging, clip, rubber band, clip. What's going to happen? You're absolutely right. This is what happens. Sorry, I should take them apart. What's going on? This rubber band is getting tired. Sorry. Here it is. So they ended up hanging. We should applaud the Russells. So you see, and all the rest of us who guessed right and who sort of tried to think. So you see that, funnily enough, there is a lot of rhyme and reason to this madness. Yeah? Method to this madness. We understand what's going on. Let me emphasize again that we indeed understand this is the beginning. And this is how, I shall say, in miniature, in a toy model, but nonetheless in a genuine miniature and toy model, this is how science starts. We feel now that we understand a lot, yeah? But we haven't started writing down anything. We have not started calculating formulas or numbers, but our brains are calculating. Okay. In order to finish, let me share with you one thing that is still unpublished and which is quite new. So far, we have been adding paper clips. I will finish very, very soon, I promise. And but I started thinking, well, can I subtract paper clips? In other words, can I start with the two paper clips that are linked already and pull them apart, unlink them by just doing this operation? Until now, those of you who are very, very careful might have observed that I was rather casual about how I slotted the paper clips. We talk about orientation. You know, you can slot the paper clip, let's say, like this, or like this, or facing left, facing right. There are lots of possibilities. None of the orientations mattered until now. But at this stage, it turns out, I discovered by trial and error, the orientation matters. So I have to do this very carefully. Please allow me a few seconds until I set it up. I'm now linking the two paper clips. And if I do it right, I do it wrong, I end up just tearing the paper. And that's not good. So I have now linked those two paper clips. This is going to work. Yeah. Okay? You see that they're linked. And I shall make the same kind of configuration, so S shape, yeah, like that. And I'm going to make those paper clips, linked paper clips, straddle over those slots that we have been using before. This one and this one. You see what I'm doing? It's a bit hard to see. Sorry, I didn't make them straddle. Here and here. Do you see what I'm doing? So those are two paper clips, and one went into this slot, the usual slot, and another went into this usual slot, but at top they are connected, linked together. Okay, so they are linked, and I'm going to push them in very, very tightly. And as I say, if I did the wrong orientation choice, I just end up bending the paper clips and tearing the paper, and I will be miserable. So let's see. I'm going to pull, and can you sort of take this picture because it's going to, and now I'm going to pull, okay? So these paper clips are linked, I'm just going to pull. What's going to happen? I hope I did the right thing. Keep fingers crossed, all crossable parts crossed. I pull. Oh, by the way, it's quite interesting. Yeah, I end up tearing the, bending the paper clips. So let me try that again. I must have done it wrong. You see, this is really an important lesson in science if I can turn a failure into lesson, because you have to learn from your mistakes. So I'm going to be a little more careful and a little less cocky this time. So here is what I'm going to try again. And I'll try this final piece of paper. I'm running out of paper, so I'd better succeed this time. So now I linked the paper clips like this. Do you see? They are linked, yeah? So there's nothing wrong with the paper clips. They are being linked. And I'm going to put them here and see if I can unlink them. So here we go. So I put them like this, yeah, and I'm going to pull. Okay, if I did the wrong thing, I'm going to end up tearing the papers, and that's the end of the show. So let's see. I pull, they come apart. So now we can subtract. What else can we do? The field is wide open, and in fact, some people, including Ron Graham and so on, and I are developing an entire science out of this. Let me finish with an anecdote. You might have heard of George Bernard Shaw, who was a great writer of Irish origin, also a playwright, especially a playwright, and also Winston Churchill, who of course was a great prime minister who led England through the war. They were sort of teasing friends. You know, they were friends, but they were teasing each other all the time. And George Bernard Shaw once wrote a letter to Churchill saying, "Dear Churchill, please find enclosed 2 tickets to the premiere of my new play. Come with a friend if you have one." And Churchill replied, "Dear Shaw, unfortunately previous commitments, I'm a busy politician, prevent me from coming to the first evening. I'll come to the second evening if there is one." One of the greatest pleasures that I have in coming to a place like this is the opportunity affords to me make so many new friends among the young people. Some of you will become my scientific colleagues tomorrow, but all of us will become my fellow inhabitants of this same planet. And I hope that I'll have another occasion to meet you again. I hope there will be a second time. Thank you very much.
We have time for a few questions, if anyone dares. I see a few hands.
Can you manage the hands? I have bad eyesight. So.
What made you come across this idea?
The question is a very good question. Is what made me think of all this? Well, as I mentioned, historically, the first just pure paperclips being linked is apparently a known trick among the community of magicians. Yeah. But in fact, I didn't know this. I stumbled on it independently. I just was playing with things, and I discovered this. And so the question is, well, what on earth possessed me to play with paperclips and a strip of paper? Well, you know, I try lots of new things. And a bit like hunting, a bit like sort of hoping for my vegetables to grow up and whatever, I sort of tried to sense where interesting things are. And maybe paradoxically, I try to find surprises in life. And that's called scientific research. You want to find surprises, but surprises that you can then play with and develop and build into and connect to the rest of the universe. And maybe after that, it's no longer too surprising because you now have understood it, but there are other surprises that this surprise opens the door to, and so on and so on. And so you have to keep going, and also you have to be patient, persistent. Of course, I failed lots and lots of times when I tried to do it. I mean, most of my trials are duds, but sometimes something interesting happens. And then I thought of adding those rubber bands and so forth. So I'm not answering the question really properly, but because it's a mysterious process. Nonetheless, it's a process that many of us can participate in. It's called research. And we can do research on all sorts of levels. For example, what you have seen today, you might think, oh, it's simple, I'll try it with my friends and family. Please do, and I hope that you discover some other things. You know, you can think of lots of variations on this paper clips and the rubber band trick. But I can tell you that it's fair to say the vast majority of scientists in the world, more than 99% of the people, would find it completely astonishing. They haven't seen it. It's not the kind of thing where, oh, big scientists already know this and we are going to simplify it for you people, you know, all ordinary people who don't understand anything, and we'll write textbooks about them. No. It's actually really surprising for seasoned scientists as well. Yeah, Nobel laureates, fields medalists, and they all find it surprising as well as you do. The only difference is that those seasoned scientists have a lot of technical baggage and preparation. So once they find a surprise, they can make a progress very, very quickly. But you can have the technical baggage as well, and then you can make progress. So I don't know how I find these things, but we all do.
Another question.
Students.
Yeah, go ahead. What southern languages do you speak?
The question is, what languages do I speak? Well, that's a professional secret, I'm afraid. But the amazing thing is not how many languages I speak, but that I don't say anything intelligent in any of them. But you have to understand also that this question, it's an interesting, so let me comment on this. The number of languages that you speak is actually a vague question. And it's a bit like asking, how many friends do you have? Well, it depends. Yeah, on what we mean by friends. And with languages, it's the same thing. For example, I have never learned Italian officially in my life. But because I know basically French is a native language for me, and I'm fluent in Spanish, and I used to do Latin as a profession. So among those three, and I know the history of Romance languages, I can open an Italian newspaper and I can read it no problem. Now, does it mean that I know Italian? I have never learned Italian in my life, but somehow it's close enough. I can kind of approach it from various angles. And similarly, you know, with friends, it's the same thing. It's not that the more friends you have, the better it is, but it's really a matter of what friends you have. And each friend also is a complicated business, right? You might be very, very close with a friend, and then you can walk apart in life, and you lose touch. But 30 years later, you might meet again, and you might become close again. And such histories also happens. Episodes happen in languages as well. So it's really not a very well-defined question. You see that I avoided answering.
Any other questions?
So maybe from a student, because I'm going to do. Huh? Do you have one last question from a student? No? No student is interested anymore. Well, okay.
How long did it take you to figure out all those combinations?
Excellent question. How patient do I have to be, and how hard do I have to work? How long did it take me to figure out all these combinations? The answer is, I'm working on, or if you like, I'm playing with, it's more or less the same thing, I'm working on lots of things at the same time. So I didn't work on this full time at the stretch, right? So I would say but one thing led to the next. And you can feel it too, right? While we're exploring this together, you are wondering, next thing, I'm going to try this. Oh, what happens? You had natural questions. You should pursue those instincts and then see what happens. Sometimes it's not interesting, but sometimes you find a surprise. So it was really a very natural progression. And I would say the total number of minutes that I actually spent was maybe just over an hour, actually. But I did it over a fairly long period. Because sometimes I come back and I think, so next time I'm going to try this, but I'm busy shopping, for example, for food. And then when I come back, I can try and so on. But you just keep it burning in your mind. But it really doesn't take long. But you have to somehow pursue it. And then you get somewhere.
Let's thank our speaker once again for an incredibly engaging talk.
Good.